Welcome to the annual Oppenheimer Lecture. I'm Frances Hellman, Chair of the Department, and I'm going to turn the platform immediately over to Marvin Cohen for all of the introductions. So, turn off your cell phones.
Welcome to the 2010 J. Robert Oppenheimer Lecture. As you heard, I'm Marvin Cohen, and it has been my great pleasure to serve on the Oppenheimer Lecture Committee since its inception in 1998. We've been privileged to have several of the world's outstanding physicists delivering lectures to us in this series. Murray Gell-Mann, Kip Thorpe, Freeman Dyson, Chen-Ning Yang, Robert Laughlin, our own Bruno Zimino, who is here tonight, Edward Witten, Martin Rees, Michael Fisher, Stephen Hawking, David Mermin, Claude Cohn-Tanuji, and today our 13th lecturer is Frank Wilczek. Our list includes 5 Nobel laureates, so we've been very fortunate in attracting excellent speakers. In the early lectures, before introducing the speaker, I would say something about Oppenheimer and the history of his involvement with our department. However, in recent years, I tend to say much less because of the wide range of media coverage and our own department displays covering his activities in Berkeley from 1929 to 1943. His former office is room 435 in Old LeConte Hall, not far from here. There are histories, letters, a plaque, and a number of memorabilia on the 4th floor of Old LeConte Hall, which I invite you to visit. For those of you who would like to learn even more about Oppenheimer, there is considerable information on the web, many books, television documentaries, and dramas, and even an opera. So his legend lives on, and we continue to celebrate his connection. This evening, we will hear what I expect to be a very optimistic talk about the future of a branch of physics that is often in the spotlight. The quest for ultimate laws to describe reality, quoting Frank's abstract, has been an ongoing goal of many theorists. And in this series of lectures, we have heard from individuals at the forefront with differing views about the possibility of attaining this goal and what it would mean if we did. As in the past, I'll begin by sharing some personal observations about the lecture subject, and then I'll tell you a little bit more about our lecturer. So let me start with Frank's comments in his abstract about ultimate laws to describe reality. I expect that he will focus on the laws and testing them. But around 100 years ago, Einstein and Mach and Bergson and others discussed the second part of Frank's statement extensively. They questioned what we mean by reality. Much of the time, I tend to be a physics pragmatist. I use quantum mechanics daily and worry less about its weirdness than many others. And I guess it's that one just gets used to it. But reality, in my view, is something for physicists to think more about, as Einstein and Mach did, and not just leave this area to the philosophers. For example, much of what we do in condensed matter physics involves explaining properties of ordinary matter using fictitious particles. You might be surprised to learn that semiconductor engineers working in Silicon Valley build electronic devices for computers and television sets by managing fictitious particles called holes, representing the absence of an electron. Why holes? Because conceptually, it's easier to use a hole to tell how a billion electrons minus 1 act in keeping track of all those other electrons. But you might say holes aren't real. They don't exist in nature. Or do they? If one takes the view that we can only know what we perceive if it acts like a hole, moves like a hole, and is what someone can use to describe what they are observing, perhaps that's all we can ever do. This sounds strange, but when asked if we treat light as a particle or a wave, you all know the correct answer is yes. We think of a hole as an emergent property of solids. concept of emergence in science has enjoyed increased attention currently, and its role in other areas of human thought has also been re-examined. Henri Bergson was an accomplished French mathematician when he argued with Einstein, claiming that Einstein's theory of relativity was wrong. Einstein convinced him it was right, and Bergson converted and became a strong proponent of the theory. Bergson then moved from math to philosophy and thought about the Einstein Mach-type ideas of reality. He proposed that all we know is what we sense, and properties or entities can emerge when you have a complex system, as in the case of the emergence of a whole, or the emergence of our speaker, Frank, who is made from more than 1 trillion cells, which all act together so Frank can emerge. Henri Bergson did some work which brought clarity to these concepts of emergence and related concepts in the early part of the 20th century. And now this way of thinking influences how we approach some areas of theoretical physics. Incidentally, Bergson changed fields again and was awarded a Nobel Prize in Literature. Emergence is an alternate view to reductionism, which is more along the lines that some theorists, particularly in Frank's area, cling to. For example, for them, a solid is made of atoms, and that's it. Whereas for some of us, a solid has many emergent particles, like phonons and plasmons and excitons and bogolubons, et cetera, So our reality may be different from theirs or yours. If Bergson is right, the connection between an ultimate theory and reality may not be so simple. We are just beginning to see these complexities in brain research. How do we go from a child's brain learning to understand the concrete world through observations and experimentation to a brain capable of abstract thought? How do we go from viewing the brain as a bag of chemicals to Freudian psychology? For example, how does psychoanalysis affect brain chemistry? And brain scans show that it does. My main message here is to assure our students that even if the Large Hadron Collider verifies the ultimate laws, there is still an enormous amount of exciting work left for them to do. If Frank's dreams are realized, you will have a better alphabet to create your own words, and physics will not be finished. Now let me tell you a little bit about Frank. First, let me call your attention to the delightful interview of Frank in the December 29, 2009 issue of the New York Times. In 2005, Frank participated in the celebration of the 90th birthday of our revered Charlie Towns. I was a reviewer of Frank's wonderful paper for the volume associated with this meeting, and by the way, the volume will be published this October. I took advantage of my reviewer position to encourage Frank to be an Oppenheimer lecturer, and in 2007, he agreed to come in 2010. I was delighted when he accepted the invitation because Frank is one of the best theoretical physicists in the world. Frank has made major contributions to physics and has received numerous awards, including the Nobel Prize. And he is fun, as you'll see, and does unusual fun things. I'll give you one example of the latter, and then I'll let him speak. In the fall of 2008, there was a conference at the Metropole Hotel in Brussels. It was sponsored by the Solvay family. This was the modern version trying to recreate the famous Solvay conferences which were at the Metropole early last century. The incredible conference picture from 1911, which is in many science textbooks, and I'm sure the students have seen this, showed Einstein and Planck and Marie Curie and many of the best scientists of the time. The picture's available on the web for those of you who are interested. When it came time to take the picture of our group, my wife pointed out to me that that was the only time my colleagues put on their jackets. It was also interesting to hear some members of the group trying to remember where Einstein was placed in the 1911 photo so they could occupy that place in our picture. But not Frank. When the prince wanted to have his picture taken with the attending Nobel laureates, Frank showed up in a T-shirt with the cartoon character Vendetta on his chest. Vendetta has a major evil role in the TV and web series Making Fiends, which I think is a spoof on the children's website, Making Friends. I saw the prince wince as he tried to figure out who or what Vendetta was. And if you look at the 2008 Solvay conference picture, you'll see Frank in the front row displaying Vendetta. So let me briefly outline tonight's program. After Frank's talk, there will be a short question period. And then just outside this lecture hall, Frank will be signing copies of his book, The Likeness of Being, which will be for sale with 20% of the proceeds going to our own Friends of Physics Fund. And so we all thank you, Frank, for your generosity. And now let me invite Frank Wilczek to come to the podium, and he will speak on anticipating a new golden age. Thank you.
Thank you, and thank you for coming. It's lovely to be here at Berkeley, where so much great physics has been done in the past. And I got today to have a kind of tour and got to see that great physics is still being done here today. And it's quite inspiring. And thank you for inviting me. So enough of that. My topic today is anticipating a new golden age. From time to time in physics, there are periods of extremely rapid progress when our basic understanding of the world is somehow changed or enriched. There were three such periods in the 20th century. There was a period of plus or minus 5 years around 1910, when the theories of relativity were developed. There was a period of plus or minus 5 years around 1925, when the theories of quantum mechanics were developed. And then a third period around 1970, plus or minus 5 years, when the cluster of ideas and theories that we now call, by the ridiculously modest title, the Standard Model, were developed. The Standard Model is, as I said, a ridiculously modest name for one of the great culminating achievements of mankind's scientific quest. It provides for ordinary matter under ordinary conditions with an extremely broad definition of what you mean by ordinary, what I think are complete, precise, economical, and in their own way, beautiful laws. The laws are based on symmetry. They are, as I said, very precise. I can quantify that in a sense. The main equations of the Standard Model emerged in the early 70s, and ever since then, experimentalists have done more and more refined experiments to try to poke holes in this theory, to find deviations, using the highest energy, most extreme conditions they could find, and making the most accurate measurements. There would surely be Nobel Prizes for finding deviations from the Standard Model. But all that's happened is that for years and years, people have confirmed the model with more and more accuracy. Nevertheless, we're not satisfied, because the Standard Model, given how powerful it is not as beautiful as it ought to be. It's close to God's last word on the fundamental way the universe works, and we expect that last word to be extraordinarily beautiful. It's economical, but it's based on describing the world as having four forces, four distinct forces: gravity, electromagnetism, and the weak and strong forces. And four is more than one. We'd like to have a unified, coherent description of all the basic interactions. And it's based on transformations of particles one into the other, of the fundamental building blocks. And if you look at how the particles transform into each other, they break into 6 unrelated pieces. 6 is more than 1. And we'd like to have a unified description of all those different pieces. Now, astonishingly, the Standard Model, as I'll describe in more depth later, suggests the way to its own transcendence. It contains patterns that seem to point to unification. And we've had ideas about how that might be done that are precise, that suggest new phenomena. And we've just been waiting for the right tool to emerge so that we could test whether those ideas are the ones used by nature. And the reason I anticipate that a new golden age is going to emerge, the first golden age of the 21st century in fundamental physics, is that the new tool is finally on the horizon. And that's what I'd like to start by describing. The new tool is the Large Hadron Collider, or LHC. So if you fly to Geneva on a clear day and look down, you might see this kind of mystic scene with a mist off in the distance, the Alps, Lake Geneva, the city of Geneva, and then you notice a very, very strange thing, this big red circle on the ground. It's 26 kilometers or 18 miles around, and that's the LHC. Now, of course, I'm joking. It's actually about 30 meters underground that there's a ring, so you don't see anything. What you actually see is just farmland. There's almost no sign of this construction on the surface. And the ring really is that big. It's 26 kilometers around. And what's happening in this ring is that protons are being accelerated to extraordinarily high energy. Their velocity is within a part in a billion of the speed of light. And there are two beams of protons circulating in opposite directions around these rings. They go around about 100,000 times a second. At a few points, they're made to collide. The beams are allowed to cross, and the protons can collide. And around those points, there are detectors that are meant to monitor and reconstruct what happened in those collisions. This is in many ways, our civilization's answer to the pyramids, but much better because it's bigger, but more importantly, because it's big, not because it's a vanity project, but because it has to be that big to do its job. It's a result of human curiosity rather than superstition, and it's filled with cleverness throughout. Here's what it looks like inside the tunnel. So looking inside the ring, this is what goes on for 26 kilometers, 18 miles. There's one after another of these gigantic magnets. These magnets are machined to within millimeter precision so that they can guide the very fast-moving protons around that giant circle. They're moving so fast that to get them to bend even a little bit so they can make a circle, even a circle that big, requires big magnetic fields, and that's what the magnets provide. These magnets, if they were ordinary magnets, ordinary electromagnets, would take up enormous amounts of energy because of circulating currents, which would have resistance and eat up the energy. To make the electric bills acceptable, and not to dim the lights of Geneva, it's necessary to use superconducting magnets, so magnets that don't have electrical resistance. Superconductors only work if the temperature is low. So all this plumbing you see around here is meant to keep the temperature of these magnets at about 2 degrees above absolute zero, even colder than outer space, which is filled by the 3-degree microwave background radiation. So this is the coldest extended object, extended area volume on Earth, in the universe, I should say, certainly on Earth and in the universe. And all this stuff has to be kept going all the time, over 26 kilometers. You see, it's an enormous job. The people who do it are heroic, and but even they sometimes get tired. This is what the detectors look like. They're also gigantic. You can see perhaps some of the human beings here to set the scale. These tiny little things are the human beings that work on this. And it's not just big, but extremely intelligent. It's packed with state-of-the-art electronics, very densely. This detector is what's called the CMS detector, where C stands for compact. This is the smaller of the major detectors. Atlas is a significantly bigger detector. But as I said, it's not only big, but packed with state-of-the-art, cutting-edge electronics. Why does it need that kind of power? Well, the object of these detectors is to reconstruct what happens in the collisions of the protons at extremely high energies. This gives you some inadequate but suggestive idea of how complex a task that is. This is a static picture in 2 dimensions. In reality, the particles come out in many different directions, and they're moving very fast at close to the speed of light. How fast they're moving is very important information about the energies they carry. So we want to measure those velocities, which are all very close to the speed of light, very precisely. So as the particles move by, you have to get accurate timing and position information as to where they were. Also, there are many different kinds of particles coming out, things with names like pi mesons, k mesons, and so forth that we've encountered in previous experiments. We know what they're like. We want to see which particle is which. So for that, we have to also monitor how much energy they deposit as they move along. Those are those red and blue marks. How much they bend in magnetic fields. Much of the size of the detector is because you need big magnetic fields to get these particles to bend, so you can tell which is which. There's an enormous amount of information, obviously, in these collisions, and you have to keep track of it to do justice to the physical process that's underlying it. It's a job that really can't be handled by humans. The information comes without help. It comes out too fast. Most of the events are deemed not interesting because they're surely described by the standard model. These are so-called peripheral events or very forward events where the beams barely touch each other, or the particles barely touch each other and just sort of scatter at a small angle. Those are most of the events, but we throw those away because we think we understand those. Even after throwing that away and making various what are called cuts to narrow down on the subclass of events that you think might not be described accurately by the standard model, the flow of information of the things you want to keep is tremendous. The storage of information is 15 petabytes per year. That is equivalent to monitoring all the telephone traffic in a city of 500,000 people talking all the time so accurately that you could reconstruct all the conversations exactly. So it's an NSA type scale of information processing. But here the information is actually useful, and you want to keep track of it, analyze it all, and really do it justice. So it's an enormous job. New computer architectures have been developed to do it that harness the power of many, many computers distributed all over the world so that it can be done at a reasonable cost. Many of the chips involved actually are game chips because they're very fast and cheap. Things that were developed for computer games, you can image processing and so forth, have the same characteristics. But they have to be, all these things have to be able to trade information all over the world, swap jobs, divide up the jobs in a very dynamic way. So it's like the internet on steroids, because they not only trade files, but also have to trade jobs and really function as one gigantic computer. This is called the grid. What you see here is about 1/1000th of the grid. This is about a tenth of what's at CERN, and there are 100 sites around the world of similar size. So all those computers are working, analyzing these pictures to try to reconstruct what they meant in terms of particles and ultimately reconstruct what they meant in terms of the underlying physical processes that caused them. I find it quite poetic that at the end of the day, it all gets fed into a little computer screen where a human being looks at it and decides what it all means. So that's a survey of what the LHC project is as a physical entity, so to speak, as an engineering project. Now I'd like to talk about what it does conceptually. What does it actually consist of as a scientific tool? Well, here's the quick explanation. The LHC is an ultrastroboscopic nanomicroscope for studying deep inner space. That is, it's in the same tradition as Leeuwenhoek and his microscopes, who looked at very small things, or at Rosalind Franklin, who wanted to look at even smaller things. Leeuwenhoek could use ordinary light, ordinary visible light photons. If you want to look at smaller things, you need smaller wavelengths of light. Rosalind Franklin wanted to analyze DNA molecules, so she needed to use X-rays, which have shorter wavelengths, so you can resolve smaller features. If you look at the pictures that Rosalind Franklin took, they don't look like images of anything. They look like these dots. And you have to do a lot of image processing to figure out what they actually mean. And in fact, Crick and Watson won their Nobel Prize for figuring out what those pictures meant in terms of the structure of the DNA molecule. So we face a similar problem. We need exotic kinds of microscopes if we're going to study what happens in space at even much, much smaller distances than Rosalind Franklin or Leeuwenhoek did. And at those short distances, most of the action takes place very quickly. So you also have to take pictures that have very good resolution in time. So it's beyond stroboscopic, it's ultrastroboscopic, and it's beyond microscopic, it's nanomicroscopic for studying deep inner space. But it should be thought of as the latest and greatest microscope or aid to vision that there's ever been. In effect, what's happening is that when these protons collide, each one is taking a picture of the other one's interior. It's getting a sample of what's inside and spitting out that information in a very encoded form that we have to reconstruct. We want to look closer at the deep interior of protons, because a major lesson of the 3 20th century revolutions, or golden ages of physics, is that what we ordinarily think of in everyday experience as empty space, what used to be called the ether and what I've taken to calling the grid, actually is far from empty, and in fact contains everything, but virtually. That is, any kind of substance that can exist also is ever present in space all the time as fluctuations of the particle and antiparticle of the substance, that the heavier the substance is, the smaller in space and time these fluctuations are, but no matter what, they're there in our equations that describe what's happening in empty space. This is what are called virtual particles, or more vividly, evanescent quantum activity, boiling up of particles for brief lifetimes that then disappear back into space. However, if you just look at empty space with your eyes, no matter how hard you try, it'll just look like empty space. We were not designed or evolved to see the quantum fluctuations. The quantum activity is spontaneous, but also limited, its fluctuations. And it's analogous to a subconscious thought or a dormant virus or magma sealed beneath the surface of the earth. Unless you look hard for it and try to bring it to mind, or put the virus in a living cell, or erupt a volcano, these fluctuations remain hidden beneath the surface. However, having studied them and knowing the equations for what's going on in empty space, we can do a little image processing and make movies of what our eyes would see if they were capable of resolving the very small times and distances necessary to see these fluctuations that are happening everywhere and every when throughout the universe. So, with the help of a computer that solves the equations for us, the equations we can check in many other ways, we can reconstruct what our eyes would see if they were capable of resolving distances as small as 10 to the minus 14 centimeters and times as small as 10 to the minus 24 seconds. These are the scales that get you just inside protons. And I made a movie of it, or more precisely, my colleague Derek Lineweber made a movie of it. So here it comes, the deep structure of reality. This is what you would see with better eyes. Brace yourself. Maybe we can turn the lights down a little. Can we? Here it comes, the deep structure of reality. Well, here it comes. It's a lava lamp. What you're seeing here is the actual calculations of the energy, the fluctuations in energy in gluon fields, one of the basic constructions of matter, the glue that holds our quarks and protons and neutrons together, how they fluctuate in space and time on those very small scales. What you're seeing is where the colors are most vivid, that's where the energies are the highest. And then the softer colors indicate regions of lower energy density. Below a certain energy density, we cut it off so you can see something. But actually, at some level, there are fluctuations. There's fluctuations almost everywhere. This is the calculated reality of what your eyes would see if they had those kinds of resolving power. Why don't we ordinarily see that? Well, it's because these things happen too fast for our eyes to resolve, and they're too small. A big lesson of quantum mechanics is that to see something, to see the things that occur in our equations and make them run, and in that sense describe reality, to see them, you have to interact with them, and you have to interact with them hard enough to affect their behavior. The Heisenberg uncertainty principle is one manifestation of this. If you want to see the position of a particle very, very accurately, you have to be able to change its momentum by an amount that goes like 1 divided by the position accuracy. So the more accurately you want to see it, the more you have to disturb it. When you go into the deep quantum world, seeing is not only an invasive process, which is what Heisenberg taught us, but in the deep quantum world, to see something, you actually first have to make it. You have to take these virtual particles, give them enough energy to make them pop out and become real, like a subconscious thought exploding into consciousness, or magma exploding into lava on the surface. So seeing is a creative process. Now, that may sound very vague and new agey, but it means something very specific in the context of the LHC and fundamental physics. To produce a particle of mass m, and remember the heavy particles are the ones that are responsible for the fluctuations that have really short distances and really short times. To produce a particle of mass m, you must supply at least the minimum energy E that particle can have, because energy is conserved. So to produce such a particle, you have to supply the energy it needs to actually exist. And the minimum energy it can take to actually come into existence, as opposed to evanescence, is, as Einstein taught us, the energy it has when it's at rest, which is m times c squared. So if we want to produce as real particles, if we want to promote these fluctuations that are taking place at very small distances to real particles that we can observe at leisure, or that we can observe at all, really, we have to supply a lot of energy into a small space, and that's why the LHC is what it is. If we want to see really small distances and really fast processes, we have to concentrate a lot of energy into a very small space. Okay, so now I've described what the LHC is, both as a physical object and as a conceptual object. Now I'd like to describe what I think and hope will be the most profound discovery made at the LHC. Many things might be discovered at the LHC, and I could give several lectures about different ones that might be discovered, but I'm only giving one lecture, so I had to pick what I think is the most important, most profound, most promising, and here it comes. Okay. This is a dodecahedron. It conveniently has 12 sides, so it can make a calendar. It's one of the regular solids. There are only a few of them that were known already at the time of the ancient Greeks, and Euclid's Elements culminated in the proof that there are exactly 5 regular solids, and showing what they were, and dodecahedron is one. Each of its sides is a pentagon, a regular pentagon with equal sides and angles, and each face, each side of it, is a copy of the same regular pentagon. This is an object of enormous symmetry in the precise sense that there are many transformations you can make on it. So rotations of that top pentagon, say, that carry through to the entire object, which change the object face by face, but don't change its overall shape. So there are many ways of transforming this object that don't actually transform it. There are many distinctions you can make that don't make a difference. And if you think about it, that's what we mean by an object being of high symmetry. So an equilateral triangle allows you to make rotations by 120 degrees, an arbitrary and comes back to itself. An arbitrary triangle doesn't. The most symmetrical object, a circle, allows you to make rotations by any angle, and it comes back to itself. There's no other object that has that much symmetry. So the dodecahedron has quite a lot of symmetry and is a very special object. And now suppose you were handed this thing. Well, you would notice that even though it's laid out flat in a plane, it consists of regular pentagons, and there are 12 of them. And you can see that if you sort of folded it, if you know about dodecahedra, you would know that this is meant to be a dodecahedron. But then suppose somebody handed you this thing. Well, now you really have to know about dodecahedra and have some imagination to imagine that this is also meant to be a dodecahedron, but somebody's taken away some of the pieces, hidden them. But if you knew about the possibility of regular solids and that there were only a few and that they involved pentagons, if you knew about the mathematics of symmetry, you would still probably be able to guess that this was meant to be a dodecahedron, but some evil spirit took away part of it. Okay? That's the situation we face in the Standard Model. We have different pieces. Different pieces, 3 different interactions, strong, weak, and electromagnetic. I'm putting aside gravity for the moment. It'll come back. But at the level of the Standard Model, they seem to be disconnected. These different interactions mix up particles in the fundamental particles in certain ways. The SU3 strong interactions mix up these particles horizontally. The weak interactions, SU2, move them vertically, and the electromagnetic, or more accurately, hypercharge interactions interact with them, but the strength indicated by these funny numbers on the side. The important thing to notice is that although many particles are related, they still fall into 6 disconnected pieces. So this is the 4 different interactions, plus with gravity ignored, plus 6 different pieces of disconnected particles that I alluded to in the beginning when I said that the Standard Model, although extremely powerful and precise and economical, we can write down essentially all of known physics on one transparency, and there it is, still has room for improvement. It looks like that dodecahedron with some of the pieces removed. And if you study the mathematics of the symmetry appropriate to these particles and interactions, you do find that if you make the bold guess that these subsymmetries that we actually observe fit into a larger symmetry that includes them all, and that these different pieces of the figure, analogous to the dodecahedron, actually should fit together into one unified figure. If you make that bold hypothesis and fill in the missing pieces, you find that it works beautifully. There are only a few ways you can do it. The mathematics of this is highly constrained, just like the mathematics of regular solids is highly constrained. And when you do that, one of the few things you can try that's reasonably simple really works. This is SO10, which comfortably but snugly fits all the symmetries of the standard model and includes a bit more. And all those disconnected pieces then click into place very beautifully. Also, those little numbers that describe the electromagnetic interactions and were just taken from experiments so that the electromagnetic charges were unrelated to the strong and weak interaction properties are now intimately and uniquely tied to them by the overlying symmetry. So it's a beautiful picture. I won't have time to do it justice, but trust me, the more I explained about it, the more beautiful it would be. But there seems to be a difficulty with this idea. That is, if the different interactions, if the strong electromagnetic and weak interactions were really facets of one more basic, fundamental interaction, we would expect that they have the same power, the same strength. In reality, they're observed not to. The strong interaction really is the strongest. So if we plot it in this funny way, so the strength of interaction increases going down. You'll see why I did that a little later. Then the strong interaction would be here. The weak interaction, actually, once you get past nuclear distances, is stronger than the electromagnetic interaction, so it appears intermediate, and the electromagnetic interaction is the feeblest, fundamentally. So it appears that this idea that all these interactions are really facets of the same basic interaction is stillborn. It just doesn't work when confronted against reality. So if we followed the philosopher Karl Popper, who taught us that the goal of science was to produce falsifiable theories, we could declare victory at this point. We made a theory that was interesting and not only falsifiable, but actually false. What could be better? But naturally, we're not satisfied with that idea, so we think harder. If we find a beautiful idea that almost works, or works in certain ways, we try to make ways of truthifying it. And now we remember that when we look and examine particles and their properties, we don't see them directly. We don't see them with completely accurate focus necessarily. We see them through the distortion of all these fluctuations in empty space. We're seeing them as fish might see things in turbulent water that's fluctuating with all kinds of distortions. And we can entertain the hypothesis then, what if we correct for these distortions and go to really short distances, penetrate all those distortions to see whether the basic strength of the different interactions at really short distances, after you correct for all the distortions, whether those might be equal. And the difference, the apparent difference we see, is due to the distorting effect of these fluctuations. So we can do that with the stroke of a pen. We can correct to see what the power of the different interactions would look like if we were able to view them at much larger distances, much larger energies, or equivalently shorter distances. Here, the beginning point is what we've actually observed, this circle, and with the LHC, we'll be able to go one more tick on this logarithmic plot. That is another factor of 10 in energy, roughly. So we'll be able to go one more tick towards very high energies or short distances. That cost about 5 billion euros, and then it gets really hard after that. But with the stroke of a pen, we can continue the calculations to much higher energies. And if we plot it in this clever way with inverse coupling strength going up or coupling strength going down, and large energy going to the right, or short distances, it looks almost like a straight line. This is basically the calculation I got the Nobel Prize for. So it must be right. All right. Okay, so now we can make a similar correction for the weak interactions and see if this idea that maybe they're fundamentally equal but got distorted can hold up, because we correct for the distortion, see if they become equal. And sure enough, they do become equal at very short distances. The lines cross. Now, and the experimental accuracy of the measurements and extrapolations is given by the width of these lines. So they really do cross. Now, maybe that's not as impressive as it could be, because you might remind me that two lines do tend to meet in a point. That's not quite fair, because a lot of things could have gone wrong. If these guys were opening up the opposite way, then it wouldn't be at short distances where we haven't explored that this purported unification occurs, but at longer distances where we have explored and we definitely know it doesn't occur, so that would surely be wrong. Also, if the unification occurred prematurely, you predict that certain rare processes like proton decay would occur much more rapidly than is allowed by experimental observations. So the fact that they unify but not too soon is encouraging. Nevertheless, and also I should say that it's a very profound fact about physics that if you plot things this way, you do get straight lines. Okay, so that didn't come for free and was partly an artifact of the way I calculated things. So it really is more impressive, but nevertheless, it's true that two lines do tend to meet in a point, so it's not as impressive as perhaps it could be. But we have a third interaction we can bring in, and we can make a crucial test then. So here it comes. Oh! Not quite. Almost. They seem to want to converge. They're moving in the right direction. But with the experimental accuracy, clearly they don't quite make it. So we're tempted to appeal to Professor Popper again and say, wasn't that good? We produced an even better falsifiable and false theory. But that's not what we do. We want to look for ways to truthify it, perhaps by making an even more beautiful theory, an even more ambitious conjecture. We shouldn't give up on beautiful ideas too easily. Maybe we haven't been bold enough. Well, we were pretty bold. Electrons and quarks, for instance, seem to be very different kinds of particles with different behaviors. And in our unification, we brought them into the same structure, so they're as similar as different sides of a dodecahedron. Photons and gluons seem to be very different kinds of particles, but we also unified them in these ideas. And I should say there are very precise equations that go with all the ideas I've been describing. However, you'll notice that even if all that works, we still have two different kinds of things. And two is more than one. So, in order to complete that unification, we would like to draw the lines between those two kinds of particles that we have unified. This can be done if we extend our model of the world to include another powerful unifying idea, not just unifying the different interactions, but unifying the different kinds of particles, to be more precise, the particles with different amounts of spin. This is the idea called supersymmetry. Now, this, to physicists pre-1974, would have seemed absolutely outrageous. It seems like saying that apples are the same as oranges. Because on the surface, Quarks and electrons, which are particles that have spin 1/2 and are called fermions, and photons and gluons, on the other hand, which are particles of spin 1 and are called bosons, couldn't seem more different. Fermions obey the Pauli exclusion principle. They refuse to occupy the same, two of them refuse to occupy the same quantum state. That's why when you try to press through a table, the electrons resist and don't allow you to, even though the table is mostly empty, atomic space. Whereas bosons, photons, love to do the same thing. Well, with a little coaxing, like Professor Towns taught us, they'll become a laser beam in which many, many photons are doing exactly the same thing. That's what bosons like to do. What electrons absolutely refuse to do, photons love to do. So it seems that these are hopelessly different and can't be unified. But Professor Zumino and his colleague, Professor Wess, taught us in 1974 that there is a way to do it, to consummate this unification in very precise, concrete equations. That's called supersymmetry. Now we can have a quasi-intuitive description of that mathematics. It doesn't really do justice to the mathematics, but it's something you can put in a picture and talk about. The idea of supersymmetry is that there's an extra dimension of space-time, but it's a very different kind of dimension than the dimensions you walk around in or experience as time. It's what we call a quantum dimension. What happens when you move in the quantum dimension is not that your position changes. That's what happens in ordinary dimensions, or your time changes. It's that you change. You change if you were a fermion into a boson. Your spin changes and your mass changes. Some things stay the same. If you had electric charge, that would stay the same. If you had color charge, it would stay the same, and so on. Some things stay the same, but mass and spin don't, and fermion and boson character interchange as you move into this extra quantum dimension. So that's the basic idea of supersymmetry. It's very non-trivial to turn that concept into equations, but Zumino and Wess and their followers have taught us how to do that. So we can expand the equations of physics that we know to describe this extra quantum dimension. And when we do that, we find that there have to be lots and lots of new particles. Basically, every particle that we know about has to have a partner that it changes into when it moves into the extra quantum dimension. With that idea, however, we can start to get a unified description that includes both bosons and fermions on the same footing. To do this, we've had to expand the equations of physics with many, many new particles. But having done that and constructed this extra quantum dimension, now we can change the apples into oranges. It's very easy. It's really fun. You can do it, and it's really fun. You can do it. Now, as I said, this brings in new particles. We just learned, however, I've told you, that everything that exists as a real particle also exists in fluctuating form as a virtual particle. So all these new supersymmetric particles also exist in fluctuating form. So they contribute to this distortion of our vision of the power of the different interactions. It's another thing we have to correct for when we extrapolate to short distances or high energies. So they make new corrections. We have to include those. We have to recalibrate the properties of this fluctuating medium to include more kinds of things that are fluctuating. And if we do that, we get a triple exclamation point result. Now they do meet. And we can put this in a much more respectable scientific quantitative form. This is the actual calculation that shows that unification hearts SUSY. SUSY is physics language for supersymmetry, for people, when people get fond of it. So unification loves SUSY. Now the unification, when we include that extra correction due to the fluctuations of this new supersymmetric particles, in addition to the ones we've known about before, now it really does work. Within the accuracy of the experiments, everybody crosses at a common point. Wow. But it gets better. I've so far left out gravity, but we can put it back in. Now, that really seems hopeless at first sight, because gravity between fundamental particles at distances we can measure practically is ridiculously feebler than the other interactions. You'll notice that the difference here between the fundamental strength of the strong interaction and the electric interaction is about a factor of 10. How about gravity? Is that another factor of 10, which would take us to the top of the screen? No, that's much more than that. How about another factor of 10? We go a little bit outside the building. Nope. How about another factor of 10? We go into the lower atmosphere. Nope. How about the moon? Nope. Another factor of 10. How about Jupiter? How about the edge of the solar system? Nope, nope, nope. How about Alpha Centauri? Nope. You have to take 40 factors of 10, 40 before you get to gravity, which takes you well outside the known universe. So I plotted it here, but you can't see it because it's well outside the known universe. Now, however, gravity responds directly to energy. So when we calculate how its strength changes, when we look at it with higher energy probes, it's not just that we have to correct for the distortions of virtual particles. Gravity responds directly to energy, so it gets stronger much more rapidly than these guys get modified. It's modified much more drastically because it responds directly to energy itself. And so you can do the calculation to see what happens to gravity, and I've done it, and it's from way outside the known universe. We complete the calculation. At the last minute, it comes in and more or less unifies with the other ones too. So on the left-hand side, we started with measured quantities and made the corrections that are required by the particles we know about and adding just the supersymmetric particles. We make those corrections with no reference to gravity. We find a unification, and then we find as a marvelous bonus that gravity happens to come in at more or less the same scale and unify with them as well. So I hope you'll agree with me that this is a fantastically beautiful possibility, that nature is singing a siren song. Is she teaching or teasing? I don't know. Here's nature, the siren. There's me. I've left the comfort of my ship of stable knowledge behind, gone to visit the siren, and is she going to kick back with those powerful fins or welcome me up, welcome us up to this marvelous new world that she seemed to be promising? Well, this is not a completely fanciful picture because LHC is going to tell us whether the siren has been teaching or teasing. The new particles that supersymmetry suggests can't be too heavy if they're going to do this job of fixing how the couplings come together. If they get too heavy, then their effects as fluctuations are too small and they can't do that job that They seem to be doing so well. So they can't be so heavy that they'll escape detection at the LHC. If we don't see them at the LHC, this whole circle of ideas falls to the ground. So there's going to be a trial by fire. Do Susie's new particles show up at the LHC or not? In the trial by fire, all these ideas might go up in smoke, or you might find that when you examine these particles, collide the protons, take the pictures, run them through the grid and analyze them to see what they're telling us. Maybe they'll tell us things like, here I am, I'm a Susie particle. Here I am, I'm another Susie partner of a known particle, and then we'll all be happy. So I hope I've given you some idea of why I do anticipate a new golden age and why this is a particularly exciting time to be a physicist. Thank you. And now we have questions?
Yes.
Now, in my experience, questions is often an awkward time and people don't know what to ask, so I have a few suggested questions. You don't have to ask these questions, you can ask me any, but here are some suggested questions. Will the LHC destroy the world? You may have read about that. What about dark matter? What's it like to win a Nobel Prize? I don't know where that "you" came from. Is there really a rap song that explains it all? So those are my suggested questions.
Is there really a rap song that displays it all?
I'm glad you asked. Yes, there is. And here it comes.
Oh yeah. I'm about to drop some particle physics in the club. The LHC is super duper fly. You know what I'm saying. Check it.
27 kilometers tunnel underground, designed with mind to send protons around. A circle that crosses through Switzerland and France. 60 nations contribute to scientific advance. 2 billion protons spinning round through the ring they ride, till in the hearts of the detectors their mates collide, and all that energy packed in such a tiny bit of room becomes mass particles created from the vacuum, and then.
Oh yeah.
LHCb is where the antimatter's gone. Alice looks at collisions of lead ions. CMS and Atlas are 2 of a kind. They're looking for whatever new particles they can find. The LHC accelerates the protons in the lead, and the things that it discovers will rock you in the head. We see asteroids and planets, stars galore. We know a black hole resides at each galaxy's core. But even all that matter cannot explain what holds all these stars together. Something else remains. The dark matter interacts only through gravity. And how do you catch a particle? There's no way to see. Take it back to conservation of energy, and the particles appear clear as can be. You see particles flying in jets they spray, but you notice there ain't nothing going the other way. You say my law has just been violated. That don't make sense. There's gotta be another particle to make this balance, and it might be dark matter. And for the first time, we catch a glimpse of what was from most of the known verse, because LHCb is where the antimatter's gone. Alice looks at collisions of lead ions. CMS and Atlas are 2 of a kind. They're looking for whatever new particles they can find. Antimatter is sort of like matter's evil twin, because except for charge and hiddenness of spin, they're the same for a particle and its anti-self. But you can store an antiparticle on a new shelf, because when it meets its normal twin, they both annihilate. Matter turns to energy and then it dissipates. When matter is created from energy, which is exactly what they'll do in the LHC, you get matter and antimatter in equal parts. And they try to take this back to when the universe starts, the Big Bang, back when all the matter exploded, but the amount of antimatter was somehow eroded, because when we look around we see that matter abounds, but the antimatter's nowhere to be found. That's why LHCb is where the antimatter's gone. Alice looks at collisions of lead ions. CMS and Atlas are 2 of a kind. They're looking for whatever new particles they can find. The LHC accelerates the protons in the lead, Those particles race straight through like a photon. It has no mass, but something heavy like the top or it's dragons. And the Higgs is a boson that carries a force. It makes particles take orders from the field that is its source. They'll detect it.
Okay, I'll stop it there. That's Alpine Cat. It's called the LHC RAP. It goes on from there. There's more, but it gets pretty dubious, into dubious speculations. Up to there, it was quite accurate and good.
Questions?
Yeah. Yes. Yes, well, astronomers, just as we sort of consolidated the standard model and we're very happy that we understood matter very accurately and very completely, the astronomers threw us a curveball. They discovered by convincing observations that what we call ordinary or normal matter, the matter that we're made out of and that we study in biology and geology and chemistry and all branches of engineering, the matter that's made out of protons and neutrons and electrons and photons, that stuff in the universe as a whole supplies only about 5% of the mass. And that surrounding every galaxy that's been studied carefully, including our own, there's a halo of stuff that can't be made out of ordinary matter, whose effect is seen only gravitationally, that altogether, however, weighs about 5 times as much as the ordinary matter in the galaxy that is in the center of it. So I talked about that as a dark matter, a halo surrounding the galaxy. It would be more accurate to talk about the galaxy as an impurity in the dark matter halo, because the galaxy is only 1/5 as heavy. Anyway, we don't know what this new material is, this dark matter that the astronomers have seen only through its gravitational influence. One possibility, though, is that when we reconstruct the kind of conditions that we're producing at the LHC, which, if you think about it, is tremendous concentrations of energy similar to what we had in the earliest moments of the Big Bang, that will produce some particles that were produced in the Big Bang and just have been around ever since, and those might be the dark matter. So if we discover a particle with the right properties, that namely it's very stable since it has to live the lifetime of the universe, weighs the right amount, and interacts very, very feebly under ordinary conditions with ordinary matter, we could make the case that that's the dark matter. And then especially if we could use the properties that we learn about it to calculate how much it was produced in the Big Bang, and got in those calculations the right answer for how much is produced, to agree with observations, we would have a beautiful concordance between fundamental physics and cosmology. And then, of course, astronomers could also go out and check whether this supposed thing that makes the dark matter really is the thing that makes the dark matter. Once you know what you're looking for, it's much easier to find it. So that's a possibility, and it's made all the more critical and compelling by the fact that many attempts to implement these ideas of supersymmetry produce a particle of exactly the right kind. The supersymmetric partner of the photon or of the Z boson or some mixture of those could easily have the right properties to provide the dark matter.
We have a question right here.
Yes.
Do you believe that the antimatter in the Big Bang might have escaped to another dimension and there might be antimatter parallel universes?
Okay, so the question is whether there are antimatter parallel universes. Well, an early version of this idea was the possibility that distant galaxies might be made of antimatter. I think we can rule that one out because from many arguments, but most directly from the fact that some cosmic rays come from very, very far away, and if they were made of antimatter, they'd produce spectacular annihilations when they reached us, which aren't observed. There have been speculations about extra dimensions of space besides these quantum dimensions of supersymmetry. And if you had a different speaker here, you would get perhaps a rhapsodic account of the possibilities of these extra dimensions. But to my perception, these constructions have not led to compelling consequences, so I doubt that they have substantial reality.
Thank you for your very interesting question. Other questions? Over there? Yeah.
It seems like in your super central graph, your four forces. It seems that the four forces intersect only in a very specific condition. So why would that lead to a unified theory that applies to everyone?
Well, okay, I think I know what's bothering you.
Could you repeat the question?
Yeah, okay, I think if I interpret it correctly, let's show the... Perhaps what's bothering you is that, okay, they meet at one point, but then they start going apart again. Okay, and that's true if you make the corrections just based on the particles we know about, or even if we add up their supersymmetric partners and make the corrections to how we should correct for distortions due to fluctuations in empty space using only those particles. However, if we made a full theory, including not only those particles, but also the particles that we don't observe directly at present or put in as partners of them in supersymmetry, if we included those particles, which have to be very heavy, then in the full theory, once the couplings met, they would stay together as you go to higher and higher energies. Okay. So I drew the results that you get only for a part of the theory. If I drew it for the whole theory, once they came together, they would stay together if we included the additional corrections due to the additional particles that I didn't include in this calculation, but that are in the complete theory.
Okay, we have time for one more question. Right here.
I was wondering about the current conflict between engineering and physics, in the sense that the LHC requires very sharp trajectories over long distances. But in geometry, Heisenberg uncertainty principle seems to prohibit that. And even quantum field theory doesn't allow sharp particle localization. How do you reconcile the theory and engineering?
Okay, so the question is, according to the uncertainty principle, roughly speaking, if I can paraphrase your question, according to the uncertainty principle, the positions of protons can't be known very precisely. So how do we get them to collide at the LHC? Right, basically that's... And the answer is usually they don't collide. These beams, when you aim them at each other, pretty much pass right through each other. It's only a small fraction of the protons in the beams that collide each time. That's one reason it's important to have a ring, so you can try to use the same protons over and over again until they do collide. So it's only when we're very lucky and in their uncertainty they happen to coincide that we get a collision.
Okay, I'd like to thank Frank for his wonderful talk and for the concert.